Hello, in this lecture I want to sort of introduce us to the biology unit by talking through some aspects of chapter 1 of the second textbook of the class, which was the McMurray textbook. There were some things that really stood out to me in this chapter, and I just wanted to kind of highlight a couple of quotes. So as they introduced us to um, the chapter, they said, none of, and if I paraphrase this point just for context, none of the tremendous advances in biology, so I'm just going to, again, kind of paraphrase for context, could occur without detailed knowledge of chemistry. Okay. Additionally, they kind of made a point that biomolecules are enormously complex, but they're still just molecules. And as such, they obey the same rules of reactivity as the molecules we've been studying so far. So sorry to get a little long-winded. I just thought this was fun aspects of the starting chapter to get us pumped up. Okay. So then they kind of go into a review of some basic topics related to organic chemistry. What I wanted to direct you towards were some less familiar functional groups. Some less familiar functional groups. So for starters, we have the RO, and then when the O is directly attached to a P, and this is going to be a phosphate. Phosphate is going to have 4 oxygens. One of them is double bonded to a phosphorus. One of those oxygens is bound to the rest of our molecule, and then the other 2 oxygens, the one that's not double bonded, are either going to be negatively charged or bonded to something else. So in this case, they are negatively charged. Now, why don't we draw them adducted with hydrogen? Well, the pKa of those hydrogens would be so low that it's probably deprotonated in most of the environments we're actually going to study these things. But it could be, you could draw it protonated, you could draw it countered by something. I feel like this makes the picture a little bit more straightforward, especially since we're going to have to, in many cases, rely on those charges for balancing other charges. So this is, again, a monophosphate, which is in contrast to a diphosphate. Now, in a diphosphate, we're going to draw the same starting structure where we've got an OP double bonded to an O, and then we're going to go off to another O, which is on a P. The P is going to be double bonded, which then finishes off with an O and a minus. Now the P should have it should have 4 O's total. So we're going to add 2 additional oxygen atoms with negative charges, and this is our diphosphate. So these things can look a little cumbersome at first to draw, but they follow a regular pattern where it goes O, P, O, P, O, and then the phosphorus generally has 1 phosphorus oxygen double bond, and then 1 to 2 O minuses, or again, OHs if you really want to. But I think it makes things go easier, especially as we go up to the triphosphate. So O, P, O, P, O. Now at the end of our phosphate chain, we're going to have an O minus. I like to draw the other O minus pointing down, and then double bond to an oxygen pointing up, and this is a triphosphate. And you don't see structures beyond triphosphates because triphosphates are inherently so unstable. They're not so unstable we don't see them. Obviously, ATP adenosine triphosphate. It's just the bond, the triphosphate bond is, or group is just not that stable. tends to break down already, so making a fourth phosphate really, makes things difficult. Additionally, we're going to talk about a high energy intermediate called an acyl phosphate. So this has that sort of monophosphate character to it, but we've got a carbonyl, and so on one side of the oxygen. So here is our acyl group. Oops, sorry for my Y there. That's our acyl group, and together this is an acyl phosphate. So it's an acyl phosphate, not a phosphonate. That would be lacking in oxygen. We don't have to worry about those right now. Okay, so we also have thioesters. So thioesters look like esters, except we have a different group 6 element, the sulfur atom, in our ester framework. Okay, so we're going to see these functional groups time and time again, and it's best to just get sort of comfortable with them. Okay, we also looked at, the authors also went over acidity, and I know we've mentioned this, but I think it's helpful to review it in the context of biological molecules. So let's focus on, and really we want to focus on their basic character. So bases in biomolecules. Okay, to really understand bases, what we want to do is not only consider their structure, like let's say I've got the hydroxide ion, and I'm going to label this. I'm just going to move the hydroxide ion down just so I have a little chart here. This is going to be my base. And then we're going to have the pKa of that kind of correlates with that base. And then we're going to have a structure of the conjugate acid. Okay, so the base I wanted to start with was the hydroxide ion again. The structure of the conjugate acid is that structure with a charge increased by 1, so -1 to 0, and then we add up a hydrogen atom to it. Now the pKa corresponds to the conjugate acid. The pK value we would want to worry about for a base would be the pKb, but I find that most people just focus on the pKa of the conjugate acid and let a higher conjugate pKa of a conjugate acid tell us how strong the base is. So the pKa of the conjugate acid of hydroxide is the pKa of water, and that's about 15.74. Okay. And if you're like, wait, isn't it 14? We'll go over that in just a second. We'll do some quant math. Okay, next we have this structure. And we want to think about this as a base. Now, this is going to be hanging off of a molecule. And in particular, this is part of the amino acid arginine. So we could see this actually quite a bit in polypeptides and that sort of thing. And this is called a guanidine, or guanidino group. Okay, this is has a high pKa corresponding to its conjugate acid. It's not as high as hydroxide, so it's not as strong of a base as hydroxide. But if we consider why its the pKa of its conjugate acid is so high, it turns out that when you protonate it, I should add a hydrogen down here. When you protonate it and seemingly get an unstable positive charge, that charge is stabilized by resonance contribution from the neighboring nitrogen atom lone pairs. So you get a stable conjugate acid, and if you have a stable conjugate acid, you're going to make for a stronger base. Okay, so we have those. Now, the guanidine is actually a stronger base than an amine. Amines are typically around 10 or so, 10 to 11, depending on the amine. And that's because when you protonate the nitrogen, you don't have as much resonance stability in the conjugate acid. But you do have more stability than you would if this were an oxygen. And we'll look at that. Okay, so it's about 10 or so. Now it's in contrast with NH3, which doesn't have an R group, and that's ammonia. The nitrogen counterpart to water, that's a specific molecule as opposed to a functional group. So that has a pKa of 9.3, again, in the conjugate acid, which is NH4+. It's interesting how they, when you've got concentrated ammonia, NH3 in water, they often call it ammonium hydroxide. But if hydroxide were formed, it would deprotonate the ammonia and just make ammonia and water. And it turns out that you can make ammonium hydroxide behave like a base for stronger acids than water, but you don't have hydroxide character present. In fact, if you add an electrophile to ammonium hydroxide solutions, you will get the adduct where the nitrogen has added onto the electrophile. So it's actually more NH3 character. And you can smell it too. I think ammonium, like a tetraalkyl, or excuse me, let me just say it this way. If you could just have the actual ammonium hydroxide, it wouldn't smell, it would be a salt. There are kind of ways to get there where you replace the hydrogens with other things. It's kind of cheating, but it doesn't smell. Whereas if you actually have smelled ammonium hydroxide, you're like, whoa, this smells terrible. And that's because, or strong, I should say. And that's because it's actually ammonia NH3 that you're smelling. Okay. So these nitrogen species are different from nitrogen heterocycles. And this is an important nitrogen heterocycle, a 5-membered ring. Turns out it is aromatic, not using the lone pair I have described, but this is my basic lone pair. But it's aromatic using the other lone pair. That one doesn't usually pick up a hydrogen because you would destroy aromaticity in doing so. But the conjugate acid has a pKa, and it looks like this, of 6.95. Now this is imidazole, the heterocycle imidazole, and this shows up quite a bit in histidine, and so it is fairly abundant in biological molecules. Now the next base that we should consider is water as opposed to hydroxide. So water has a is not that strong of a base because the hydronium ion H3O plus has a pKa of -1.74. So it's fairly acidic as its conjugate acid. Alcohols like methanol, for example, they would form MEO and then having an H2 present on the alcohol. These are even stronger acids, the conjugate acid of methanol, with a pKa of -2.05. But they beat a ketone because putting a hydrogen atom on a ketone gets you a pKa of -7.5. The ketone really doesn't want to hold on to that hydrogen for long. Okay, so these are some acids, or excuse me, these are some bases. And what we notice, if I kind of pull out, if I zoom out here, you can look at all of them. I introduced these in order of descending pKa of the conjugate acids. So these are actually in order of strongest base to weakest base. We start up at the top. Hydroxide is the strongest base. Why is it the strongest base? Well, its pKa of its the pKa of its conjugate acid is the highest, so it's less likely to give up its hydrogen atom. The conjugate acid is, which means if you have the conjugate base, you have already removed that hydrogen. It's going to be desperate to get a hydrogen back. So the higher the pKa of the conjugate base, conjugate acid, the stronger the base. So we could say, we could have like an arrow of increasing base strength. Going along here. So I just put a little arrow indicating that we're going up in the strength of the base. I'm just going to make a new page here. Zoom in. Okay. So those are our Bronsted acids. Now, one thing that may be a little puzzling is how do we determine the pKa of water? Okay. And I said the pKa was equal to 15.7, and that's a nice number to keep in mind, 15.74 as opposed to 14 or whatever. Sometimes people think it's 14. Well, let's just go through that math quick. So why? Well, pKa is equal to the negative log of the Ka. Okay, well, what's the Ka? The Ka is equal to the concentration of our H plus, which is H3O plus, and the concentration of our OH minus divided by the concentration of our water. And I like to simplify my life and just put H plus. Okay. Well, it turns out that the concentration of, well, okay, I don't know. Maybe let's just keep it H3O plus. That's what they use in the book. Okay. Well, it turns out this top part is just Kw, which is equal to 1 times 10 to the to the minus 14. Okay, 1 times 10 to the minus 14. So this is the concentration of the H plus and the OH. Well, neutral water, because neutral water has a concentration of H3O plus equal to 1 times 10 to the negative 7, which is, if you recall, the pH of water, pH equals 7. And similarly, if we're at neutral water, then our OH is equal to that. So we have 1 times 10 to the negative 7 times 1 times 10 to the negative 7. That becomes then 1 times 10 to the minus 14. So 10 to the minus 7 times 10 to the minus 7 equals 10 to the minus 14. Okay, a lot of math, but we're at 1 times 10 to the minus 14 for the numerator here. What about the denominator? That's kind of an interesting one. It's the concentration of water. And you might be thinking to yourself, okay, concentration of water in what? I'm saying, let's just think about the concentration of water. Let's turn water into a concentration. And so for a second there, that might not make sense. Like, is water the solute or the solvent? And the answer is kind of both. Okay, let's break this down. What's concentration again? Concentration is moles per liter. That's our molarity. Okay. So what we want to do is figure out the molarity of water, because molarity is a nice SI unit for us to use. Well, what I'm really getting at is how many moles are in a liter of water. Okay, so let's think about this now. The density is equal to 1.0 grams per milliliter, right? 1.00 grams per milliliter, or 1,000 grams per liter. Well, look at that. We've already got half of our unit. We've got the liter component of our concentration. How do we get the moles? Well, we know it's water, so its molecular weight is 18. The molecular weight of water is 18. Okay, so what I want to do is take 1,000 divided by 18, and then I want to divide this by and then this is divided by 1 liter. This is my molarity. Okay, so let's go ahead and solve that. Sorry, I'm not doing good with my page management here. Let me get that in front of you again. Okay. Okay, so we have 1,000 divided by 18 divided by 1. That's our molarity. If I try to do that math really quick, so 1,000 divided by 18. So that's 55.55555. I'm just going to write 55.6 moles per liter. Or you could say the concentration now of H2O is equal to 55.6 molarity. Okay. So we figured out that that's kind of a useful trick, figuring out the concentration of just something. Like if you've added dichloromethane to your reaction, or you've added whatever, it's just nice to know the concentration of that thing. And that's just taking it by itself and figure out how many moles of it are in a liter. All you need is the density and the molecular weight, and you can solve for the concentration of anything, which is, I think, kind of nice to use. Okay, 55.6 is pretty high. It turns out that many things are kind of on the order of like 10 to 20. But that's water for you. Okay, so 55.6. So what we can do now to determine the Ka of water is take the Kw, which is equal to divided by the concentration of H2O, which is equal to 1 times 10 to the minus 14, which is the pH and the POH at neutral, 1 times 10 to the minus 7, times 1 times 10 to the minus 7, pH and POH at neutral water. I'm going to divide that by 55.6, and I get some number here. Let's see. That's going to be tough for me to pull off without a calculator. Sorry. I'm not prepared. Let's see if my little calculator can handle that. So 1e to the negative 14 divided by, okay, so it's 5.5 points, let's just do this, 55.6. Okay, so I think if my Apple calculator's got it good, we're at 1.7986 times 10 to the minus 16. That looks right. And now what I want to do is take the negative log of this, and that should be the pKa of H2O. Whew. All right, so I still have this in my calculator. So I'm going to take the negative log of this, and okay, my calculator is working, or is at least consistent with my lecture notes, because I have now a pKa equal to 15.7. Okay, which is what we had. 15.74 is what it adds up to. All right, so there's the math for you and how we get the pKa of water. Note it's different than the Kw or the pKw. The pKa of water is not 14, it's 15.7, okay? That's helpful for understanding these scales, but it's a nice little lesson to see, and we go through this in the first part of the book. Okay, in upcoming lectures, in the next lecture, I'm gonna go through some of the interesting reactions that caught my eye while I was going through chapter 1 and these common reactions of biological molecules before we move into aspects of chapter 2. So that'll do it for this one. I'll see you next time.